Hello everyone, so today we're going to go over section 7.4 part B, equations and graphs of trigonometric functions. Today we're going to go over the word problems in the unit, starting with example 1. So the electricity coming from power plants into our homes is in alternating current. So that means the direction of the current is flowing back and forth. In Canada, it makes 60 complete cycles per second, and the voltage can be modeled using this function right here. So in the first question, it asks for the period of the current in Canada. It looks like it's already given to us here, 60 complete cycles per second. But we also want to look at how that is embedded in the equation itself. So we have b is equal to 120 pi in this question. And recall that the period is equal to 2 pi divided by b. So in this case, we have 2 pi divided by 120 pi. And we have that the period is equal to 1 over 60. And the unit in this question is in terms of seconds. So this is 1 over 60 seconds. So that means, once again, that we have 60 complete cycles in 1 second. Okay, so that is also known as 60 hertz. Sorry about that. Okay, so if we were to graph this function, the dependent variable is y, and the independent variable is t from the equation that we have. So we know that v is equal to 170 sine and then 120 pi t. That means we know for this question that the a value is 170, the b value, as we saw before, is 120 pi. And from there, we have that c is equal to 0, which means there's no phase shift, and also d is equal to 0, so there's no displacement. Okay, so we also know, because a is 170, that the amplitude for this function is 170. The period we saw earlier was 1 over 60. And again, no phase shift. And no displacement. What that means for the graph is that the maximum value that the graph will reach will be 170. And the minimum that it'll reach is negative 170. And in between the two is the midline of 0. So we have something that looks like this. This is 0, positive 170, and negative 170 volts, respectively. So in terms of time, we know that the time will start at 0, and we are to draw 2 complete cycles. So after the first period, this will be 1 over 60 seconds. And at the end, this will be 2 over 60 seconds, or 1 over 30 seconds. Oh, sorry about that. Okay, so this is 2 over 60, which is equal to 1 over 30 seconds. Okay, so given that we are working with a sine function, the sine function starts at 0, and then it will be at the 0 again, or the midline again, at the halfway point, and it will end the cycle at the midline. Okay, and then it will repeat itself. And so we know that at the start, the middle, and the end of the cycle, the voltage will be on the midline. And then in the second period, it will be, again, midline, and the halfway point midline, and then it'll end on the midline. At the end of the first quarter, or at the first quarter mark, the voltage will be at the maximum, and the third quarter mark, it will be at the minimum. And then the cycle will repeat itself. Okay, so at the beginning, the voltage will go up to 170, and they'll come back down towards 0, and it'll be negative 170, and then it'll be back at 0 at the end of the first period, and then go back up to 170, go back down to 0, reach to negative 170, and then at the end of the second period, it'll be at 0 again. Okay, so the question also asks, what are the two axes represent? This here is, of course, the voltage in volts, and on the side here, this is time in seconds. Okay, so afterwards we have part C. Suppose you switch on a heat lamp on an outdoor patio. The heat lamp requires 110 volts to start up, so we're looking for the time at which the voltage reaches 110 for the first time. So we'll start with the function. V is equal to 170 sine 120 pi t. And we're looking for when V is equal to 110, so we can just substitute that into here. 110 is equal to 170 sine and then 120 pi t. We can divide both sides by 170. Okay, so the left-hand side will simplify to just being 11 over 17. And the right-hand side would just be sine 120 pi t. And then we can take the arc sine of both sides. So we have arc sine of 11 over 17 is equal to just 120 pi t. Okay, using our calculators, we can find that the value of, arc sine, got the one there, is 0.704, and that's going to be equal to 120 pi t. And then we can divide both sides by 120 pi. And so we get t is equal to 0.0019 seconds. So that's really quick time to get a heat lamp to start up when the switch is turned on. Okay, so the first example here, we are given the function, and of course there are going to be questions where we're not given the function, so let's look at one of those examples together. Let's see here. So it says, one day at the seaport, high tide is 9.4 meters, first reached at 7 a.m., and then the low tide is of 2.6 meters and occurs 6.2 hours later. So we're going to draw a graph to make sense of the information that we're given, kind of like what we did in the previous example. So in this case, the horizontal variable is going to be time once again, just like before, and the vertical one is going to be the water level, and we'll just call it height, so H for height. Okay, so we know that the high tide is at 9.4 meters. Go ahead and draw that in. And then the low tide is at 2.6 meters. So this is the 9.4 meters at the top. And it's Then make a little bit more space. There we go. So we can write the unit in there, and then 2.6 meters is the minimum. So first thing we're going to do is find out where the midline is, or the middle water level. So this will be 9.4 plus 2.6, and then all of it would be divided by 2. And so we'll get 12 divided by 2, which is 6 meters. So this is the middle water level. Okay, so go ahead and draw that in here. Okay, so this is 6 meters. So next up we have the time to consider. So the time is going to start at midnight, so that will be 0 hours. And then 7 a.m. will be somewhere around here, so we'll just call this 7 a.m. So that's when the first high tide is going to be. So I'm going to mark that on the grid here. And then the first low tide is 6.2 hours later. So this will be 6.2 hours after 7 a.m. So we'll just say this is 13.2 hours compared to the start of the day, if the start of the day is at 0. So that'll be a low point. And we're going to assume that this tide is going to behave like a sine or cosine curve. So the next high tide will be another 6.2 hours later. So another 6.2 hours later, this will be 19.4 hours. Right, so again, how that worked out was 7 plus 6.2 gives 13.2 hours is the low tide of the day. And then if we take 13.2 and add another 6.2, that will be the next high tide, 19.4. So that's just the second high tide. Okay, so we also know that the first quarter mark is going to reach the midline, and then at the third quarter is going to reach the midline. It behaves just like a cosine function that was shifted 7 to the right. Okay, so let's just draw that in. Again, this is a very rough sketch of what's happening. Sorry about that. There we go. And this is exactly one period or one cycle of the tides. So with this graph, we can write a sinusoidal function that models the situation. That we now know what the period is. From one high tide to the next, it has been 12.4 hours. Just going to go ahead and write that in. So the period is 12.4, and we know that it's because of a high tide to the next high tide. If the question was worded so that we have only the high tide and the low tide, then we will take the time difference and multiply that by 2. That's kind of what we did. We just mathematically figure out when the next high tide is. So very similar. So the next part is the displacement. We found that that is the mid water level, so that's 6 meters. So it's just 6. That's, of course, it's a midline or the center line. And we also have to find the amplitude, and the amplitude is going to be 3.4. Recall that the amplitude is the distance between the maximum value and the midline. So in this case, it's 3.4. Also, the distance between the midline and the minimum value, which is, of course, also 3.4. So I'm going to write down how we found it. It's 9.4 minus 6. Finally, the phase shift is 7 hours. Now, notice that if the way that the graph is drawn, it starts at the maximum value, and we know that the kind of sinusoidal function that starts at the maximum is, of course, a positive cosine graph. So we're going to use the phase shift of 7 hours and use positive cosine to write our equation for this question. So all of this combined, then we have, let's see here, h of t, so height in terms of time, is equal to the amplitude of 3.4, and then this is a cosine function. The period is 12.4, so if we were to write this in our function, this should be 2 pi divided by 12.4. That's one thing that we need to be very careful about, and that is the period is not the b value. 2 pi divided by the period, that's the b value. So here, recall that this is 2 pi divided by the period. And then from there, we have the phase shift. It was t minus 7, and finally plus 6. So again, this is the a value, 2 pi over b, which is equal to the b value. The phase shift is the c value, and the d value is the vertical displacement. So this is, of course, not the only way to write the equation. We could also write this using a negative cosine function if we want to start at this time instead. Recall that the negative cosine function starts at the minimum value, so if we wanted to, we could have the equation h of t, and that's going to be equal to 3.4. That's the same. Sorry, that's not the same. We want negative cosine, so this would be negative 3.4, and then cosine, and then 2 pi over 12.4, and then t minus 13.2, and then plus 6. Another note here is generally we can simplify this to just pi divided by 6.2, or leave it as 2 pi divided by 12.4. That those two values, of course, are equivalent to one another. Okay, so the next part, it says determine the height of the tie at 4:30 p.m. So the first thing is we wrote time in terms of decimals. So for example, we didn't say hours and minutes. We said 13.2 hours or 19.4 hours. So in order to use this function that we have to rewrite the time 4:30 p.m. As a decimal time. So how would that work? So here we have 4:30 p.m. So using a 24-hour clock, we know that 4 p.m. is 16 hour, or the 16th hour, and then the 30 will be half an hour. So this is 16.5 hours from midnight. So it says to determine the height, so we are given the time, so we simply have to substitute 16.5 in for t. So we'll have 3.4, and then cosine, going to use the simplified b value here, pi over 6.2, and then this will be 16.5 minus 7, and then plus 6. And using a calculator to evaluate all this, we'll get 6.34 meters. And of course, it's important to make sure that the calculator is in radian mode for this, because of the fact that we wrote the b value in radians. Okay, so next part, it says determine one of the times when the tide is 5 meters. So this is kind of the reverse of part C. In part C, we're given a time, we're asked to find the height. Here we are given the height, and we're asked to find one of the times because the time at which the tide is 5 meters is not unique. So here we go. Here's the next part. So we'll substitute 5 for the height, and again we have 3.4, and then cosine pi over 6.2, and then this will be t minus 7 plus 6. So the first thing we can do here is subtract both sides by 6. Let's go ahead and do that first. So the left-hand side will be -1, and the right-hand side will be 3.4 cosine, and then pi over 6.2, and then t minus 7. So just one step. And then next thing we can do is divide both sides by 3.4. Right, so just like any other trigonometric equation, we are trying to get the trig ratio to equal to some number. So in this case, on the left-hand side, we'll have -1 over 3.4, and that's going to be equal to cosine pi over 6.2, and then t minus 7. From there, we take the arc cosine of both sides. So here we have arc cosine of -1 over 3.4 is going to be equal to pi over 6.2, and then t minus 7. And then afterwards, we can simplify this a little bit more. We can multiply both sides by 6.2 over pi, and then from there also add 7 to both sides. So we can rewrite it so that t is just going to be equal to 6.2 over pi, and then arc cosine of -1 over 3.4, and then afterwards plus 7. And if this were evaluated on a calculator, that will give us 10.689. So what we can do is, well, 10 parts means it's 10 a.m. And then we can take the decimal part, which is 0.689, and multiply it by 60, because there are 60 minutes in 1 hour, and that will give us 10:41 a.m. So that's one of the times where the time will be 5 meters. Okay, so of course the other times can be found by using the different quadrants. So for example here, when we got to this step, we have that cosine is, the cosine ratio is negative, so that will be in quadrants. We can determine what quadrant that is in, and then use the reference angle and find the two different values and do the question that way, and then we can find all of the times where the tide is 5 meters. But for now, it just asks for one of the times, and this answer here is sufficient. All right, so the next part is the Ferris wheel question. So here it says Ferris wheel with a radius of 14 meters is center 15 meters above ground. It rotates once every 32 seconds. A person gets on at the bottom of the wheel at t equals 0. So we're going to draw a graph once again to see the height as the time goes by. Okay, so we are given that the center of the Ferris wheel is 15 meters above ground. So that means our midline is going to be at 15 meters. So again, this is the height. Sorry, that was very poorly written. Okay, so this is the height. This is the time. This is going to be 15 meters. And then it reaches a maximum height of 29 meters. And the reason we know that is because the radius of the Ferris wheel was 14 meters, so it would go up by 14. And then, of course, the Ferris wheel also goes down, and it will reach a minimum height of 1 meter above ground. That being 15 minus 14. So the maximum height is 29 meters, and the minimum height is 1 meter. It says that the person gets on at t equals 0. So let's mark that down. Here it goes. And what else we know? We know that one complete cycle is 32 seconds. So at the end of the 32 seconds, the person who is on the Ferris wheel will be once again at 1 meter above ground. At the halfway point, and that is halfway from 0 to 32, the person will be at the maximum height because of how sinusoidal functions work. So this will be the 16-second mark. So let's just write seconds in here as well. So this is 32 seconds here. And finally, at the two different quarter marks, we'll have the height being on the midline. So this is 8 seconds in, the person will be 15 meters above ground, and 24 seconds in, the person will also be 15 meters above ground. Okay, and then what we can do is connect the points together as a sinusoidal curve. So something that looks like this. Okay, so if we are to write a sinusoidal function that models the situation, then the period we know from above is going to be 32 seconds. The vertical displacement was 15. The amplitude was 14. And the phase shift now, of course, depends on what kind of trigonometric function we want to use. So there's 4 possibilities. It's either a cosine function that's positive, a cosine function that's negative, a sine function that's positive, and a sine function that's negative. Those are the four possibilities. So if it is a positive cosine function, then it should start with a phase shift of 16. So right here. If it is a negative cosine function, then it starts from the minimum value of 1, so the phase shift will be 0. A positive sine function starts on the midline and moves upwards to the right, so that will be at 8 seconds. And finally, a negative sine function starts on the midline as well, but goes down towards the right, so this will be 24 seconds. Again, all 4 of those are possible. So what we can do here is write all 4 of the functions. So the other piece to notice is the different values of the function. So in this case, we know that b is equal to 2 pi divided by the period. So it's going to be 2 pi divided by 32, which of course simplifies to pi over 16. Displacement is the d value, so d is 15. Amplitude is 14. Now, we're going to write it as the absolute value of a is equal to 14 because, of course, a could be positive or negative depending on what phase shift we want to use. So the 4 possible functions are, first one, h of t is equal to 14 cosine pi over 16, and then t minus 16 plus 15. So that's one possibility. A different possible equation is h of t is equal to negative 14 cosine pi over 16 t, and then plus 15 because the phase shift there is going to be 0. And then the 2 different sine function we could write. The first one is h of t is equal to 14 sine pi over 16, and then t minus 8 plus 15. And finally, the last one, h of t is equal to negative 14 sine pi over 16, and then t minus 24 and plus 15. So generally, we will be using the negative cosine function for a Ferris wheel question such as this, just because we don't have to deal with the phase shift part. So next part, it says here, determine the height of the person at 10 seconds. So we are given time. Here we can then simply substitute h of t as h of 10. And then we have negative 14 cosine, and then pi over 16, t was 10, and then plus 15. So we can evaluate this, and using a calculator, the person will be at a height of 20.36 meters. So if we are to go and look at our original graph, that time it makes sense because it's somewhere around here. So we expect the person to have achieved a height that's more than 15 but less than 29. So 20 seems to be a reasonable answer. Okay, part D. Determine one of the times when the height reaches 12 meters. So we are actually going to go and change this question slightly. We're going to find all the times at which the height is 12. So how this is going to work is we're going to let h equals to 12 and solve for t. So again, 12 is equal to negative 14, and then cosine pi over 16t plus 15. Subtract 15 from both sides, so the left-hand side we have negative 3. So negative 3 is equal to negative 14 cosine pi over 16t. Next step, of course, is to divide both sides by negative 14. Oh, sorry about that. And then so we'll have 3 over 14 is equal to cosine pi over 16t. Notice here that 3 over 14 is positive, so we have a quadrant 1 answer and also a quadrant 4 answer. So in quadrant 1, okay, we can simply go pi over 16 is equal to, pi over 16t is equal to arc cosine of 3 over 14. And what that would tell us is that pi over 16t is equal to approximately 1.35 on a calculator. So since this is a quadrant 1 answer, we can also use it as the reference angle. Okay. If this ratio was negative, then we will have to take the absolute value in order to find the reference angle and work with that angle instead. But here, then that means our quadrant 4 answer is going to be just pi over 16t is equal to approximately 2 pi minus 1.35. So that will be approximately equal to 4.93. And then we can solve for t in both cases. T in the first case is going to be equal to 6.9 seconds. Again, that's approximate. And in quadrant 4, the answer that we get, once we take 4.93 and multiply it by 16 and divide by pi, we'll get 25.1 seconds. And so within one cycle, let's just go back to the top. So think about what is happening here. So what we essentially did was there is a line to be drawn here where the height of the Ferris wheel is 12 meters. And as we can see, it crosses the graph twice, once here and once on the right-hand side. And so what we found is that the first time it crosses is 6.9 seconds. And then on the other side, this is 25.1 seconds. So within one cycle, those two will be answers. So when the Ferris wheel goes around again, in the next cycle, those two answers will repeat. So to find the general solution, or to find all the times where the Ferris wheel reaches 12 meters, we simply take our two answers and then we add the period, which of course is 32 seconds. Where n is an integer in both cases. And here as well. So that's an example where there are general solutions even in a word problem. for a trigonometric function. And that's covers all of the different word problems that we'll generally encounter in this unit. And so that's it for today. And once again, thank you for listening.